And now we're going to talk about equilibrium. This section of the course is called Equilibrium Thermodynamics. And we talked a little bit about equilibrium at the very beginning of this section, but now we're going to look at it in a little more detail now that we know about things like free energy and chemical potential. These first three we talked about before at the very beginning of the course, and here's another one we're going to add. Let's first review these three things here. System no longer evolves with time, or if you're looking at a chemical reaction, no product is formed or no reactant is used up in a chemical reaction when the reaction is at equilibrium. Just to review what we mean by this, what we're going to measure is, let's take a simple reaction A, which is in equilibrium with B. And over here we'll measure the concentration of A or the concentration of B as a function of time. So we can do this, measure these concentrations spectrophotometrically or something like that. And let's say at time equals 0, at the start of the reaction, the concentration of A is some concentration, say A0, and the concentration of B, say, is 0 at time equals 0. This concentration is A0, and initially this is 0. So as the reaction goes on, A is converted into B, so the concentration of A decreases, but then it levels off, like that. The concentration of B, initially at 0, then increases like this, and then it levels off. So the region here, where there's no change in concentration in a chemical reaction, this says this would be at equilibrium. And these lines should just be straight, they're not changing at all. So that's what we mean by system no longer evolves with time with the specific case for a chemical reaction. Let's look at energy. Energy is at a minimum, and we said from our introductory chemistry, the energy we're interested in at constant temperature and pressure is the Gibbs free energy G, and this will define more clearly later, but let's just call this the extent of the reaction. Okay, so over here you have lots of products, over here you have lots of reactants. So at various places along the chemical reaction you can measure the Gibbs free energy G, and what you find is that there's a place where the Gibbs free energy is minimum, and at that point, at that extent of the reaction, where you have a certain amount of reactants and products, you're at equilibrium. There are no gradients in intensive variables, and therefore no fluxes of corresponding extensive variables. We talked about this a little bit. Let's take, say, variable electric potential. For instance, if you have a battery, and you hook this up with a wire, electrons will flow. That's the extensive variable that's associated with the electric potential that you have in the battery. Electrons will flow from a high region of electric potential to a low. So for example, when you're not at equilibrium, if you look at the electric potential, we'll use a simple psi, and this is some spatial coordinate, some region of space, and over here you have a high electric potential, and down here you have a low electric potential. Electrons will flow in a region of space where their electric potential is large, like over here, and they'll flow down to a region where their electric potential is low, like over there. If the system is at equilibrium, the plotted potential versus some spatial coordinate will be flat. So now nothing's happening. If you have an electron right here, there's no potential gradient. Potential gradient is related to force. So there's no force to move these electrons from one place to another. So the system now is equilibrium when there's no gradients in an intensive variable, and therefore no fluxes of the corresponding extensive variable. And now finally, given our criteria of spontaneity that we talked about 2 lectures ago, we said that a criterion of spontaneity is that entropy increases. Spontaneous ds of the universe or isolated system is greater than 0. So things will keep happening until this criterion is no longer met. So let's just see. Let's look at, here's entropy, And here, well, I don't know, what do you want to put here? Time, perhaps. So the entropy will go up and then reach a maximum. So right here, you're at equilibrium. And here, ds is equal to 0. ds is slope. The slope is equal to 0. So there's no spontaneous change. The system is at rest, equilibrium, no reason for it to change. So it's just hanging out here at equilibrium, hanging out here at equilibrium. Maybe we have a little better understanding of equilibrium in general